So welcome to this new series on basics of pybamm. In this video, we'll talk about getting started with pybamm, covering how to install pybamm, how to select models like DFN, SVME, etc., perform simulations, and basic plotting options within pybamm. So let's get started. To begin with, we need to install pybamm. So we can do pip install pybamm. For me, it's already installed, so it might be quicker. But for the first time, it might take some time to download all the files and install. Once it's done, it should say install successful, and then you can move on to importing pybamm. Just a quick check if the installation was successful, you can do import pybamm, and then if it shows a green tick, you're good to go. Now, the first step we need to define is the type of model we want to use. So before solving anything, the pybamm needs to know what model should be used in the background, whether it's a DFN or SPME, SPM, ECM, etc., so that it can use the governing equations in the background accordingly. So step one is defining the model. We can say pybamm.lithium-ion.dfn, Doyle-Fuller-Newman model, also known as P2D model. Now, as a prompt or a preview, you will also see the list of attributes it can take in. So you can see here it takes options. If you want to like activate some of the default some of the modes which are by default off, like for example in DFN by default the thermal model is turned off. It's lumped. It's like a constant temperature model. But if you want to solve for temperature, you can also do that with these options setting. We'll look at that later. For now, let's use the default model, and there we go. So we are able to add it to the model variable. So this basically creates an instance of DFN model, and that is being stored in a variable which we are calling as model. We can call it anything like DFN as well if needed. Doesn't matter. Next, let's now define the simulation. So sim equals to pybamm.Simulation, and let's see what it takes as input. So simulation takes model. Now, if you see here, the one which appears in orange is the must-have input or the recommended input, and the others are optional. So it takes model, which is what we defined here, DFN, experiment, which could be the definition of how we want to run the simulation, whether it's a constant current discharge, CCCV, drive cycle run, and so on. Parameter values, so whether we want to go for default parameters or some inbuilt library parameters of pybamm from some literature, and so on. So we'll come back to these options in a separate video. For today, let's focus on basic model run. So sim equals to pybamm.Simulation, and we need to pass on the model DFN. Next, once the simulation is set up, we can then create a solution sim dot and then call out sim.solve. So sim.solve requires a t-eval parameter, which is just for how much time you would like to solve the simulation. So we can just say 0 to 3600. There we go. So we are able to run the simulation, but we don't see any plots yet. So for plotting, we just need to call out sol.plot, and there we go. So we see a bunch of different plots. Now we don't have to be confused with what each of these means, but let's just focus on the type of plots that we see. So one type of plot is just a simple plot with x as thickness. So here x value represents in micrometer the thickness across uh, the intersection, or rather the cross section of a jelly roll. So the cross section of a jelly roll consists of current collector, uh, anode, separator, cathode, and then cathode current collector. So the definition here is uh, x value starting from 0 all the way till the end of the negative electrode. So here we can see 0 to around 90 or 85 is the negative particle, which is the anode, and then the positive particle shows the value starting from this 100 mark on all the way till end of this dimension. And in the middle you see this line separator. This is the separator section. So this is anode, separator, cathode, and you can see respective plots on left and right for negative and positive particle. Similarly, we can see a current value here, which has value of time, and similarly voltage has a x value of time. So these two are time-based plots. The other ones are thickness versus the quantity being plotted here. So we see negative electrode potential, electrolyte potential, positive electrode potential, and so on. Now there is a slider which basically affects these outputs. So what you see here as 0.16 is the normalized time. So the end value corresponds to 1, which is 3600, and 0 corresponds to this value. And as you move this slider, you see a dotted line for the time-based plots. For the distance-based plots, the plots itself vary or change dynamically to account for the effect of time. So this way you can visualize some of the basic plots, predefined plots within the pybamm interface. Next up, we can look at how we can define a quick experiment. So to do that, let's define something called exp equals to pybamm.Experiment, and then we need to define it. The syntax is very easy. Just open parenthesis, and then within quotes, in plain English, we need to type in discharge at 0.5 C. Now, by default, the current value that you see here is 1 C. So 1 C is around 0.7. So if we do 0.5 C, it should be around 0.35. So let's see. And we need to define the end duration as well, until what point we want to discharge at this C rate. So we can say until 2.5. So uh, it looks very easy to be defined. And similarly, uh, we can define other conditions with separated by commas. So if you want to do discharge followed by a charge at 1C until 3.6 volts. So this is how you would define it. And next we just need to pass this experiment as is. And now since we are stopping based on these voltage values, so we don't need a time duration anymore, we can remove it and then run this. Now you can see on the right the value of current. Maybe we can increase this to 4.2. So you can see here, the current value was initially positive, which is discharge, and then became negative at 1C. And then at the bottom, you can see corresponding voltage response and the other distance-based plots as well. So that's how you can simply create a simple simulation with pybamm and get started. So thanks for watching. See you in the next one.